Hi, thanks for joining me today for our discussion on magnesium sulfonate treatments for heavy fuel oil, specifically ATX-1400T and ATX-1100T from Bell Performance. I am Eric Bjornstad. I am the Technical Information Director here at Bell Performance. And typically in any discussion like this, what we would do is we would start off by discussing the problems that HFO-fired facilities, HFO boiler-fired facilities, the kinds of problems that they typically might have. Only after we consider these problems do we have really the proper context to look at solutions to those problems. So for our purposes today, what we want to look at is we want to look at boiler tube depositing. We want to look at corrosion issues, both high temperature and temperature corrosion. We want to look at the issue of loss of operational efficiency for boiler-fired plants. We want to look at opacity and how it relates to SO3 and NOx formations. And we want to look at air preheater pluggage and what they call high delta P, in other words, heat transfer rates. We want to consider each of these kinds of things. So start off with, within the typical boiler unit itself, we have a few things going on that directly relate to problems seen by users of heavy fuel oil. In this schematic, you've got different areas where the fuel is transported, it's mixed with air, and it is burned in here. That's the transport, reaction, and formation area. After that, you get ash that forms from the inorganic compounds or components in the fuel that do not burn combustion. Ash, as you can see, ash-forming constituents are released during combustion, and they form in here. All of this is going on. You have different kinds of deposits being formed, some of which are pretty strongly associated with corrosion problems. So when we consider what we need to do to create the most problem-free HFO use experience, these are all areas that we need to look a little more closely at. Now, the industry standard for addressing these kinds of issues has usually been some kind of magnesium treatment added to the fuel oil. Magnesium treatments like these have been used in the industry for decades, since at least the 1950s. And magnesium additives have been proven pretty effective at doing things like reducing boiler depositing, cutting down on high temperature corrosion. They're very effective at reacting with the vanadium components in the fuel to increase. We've got eutectic melting points, to increase the melting points of the deposits and change their physical consistency. And magnesium additives have been shown to help contribute to the improvement of efficiency and helping to maintain a clean boiler system. In other words, keeping deposits from building up on metal surfaces to the extent that the deposits will start to negatively affect efficiency. Magnesium deposits reduce sulfur oxide formation because they contribute to this basic chemical reaction. Magnesium oxide, or MagOx, plus sulfuric acid yield innocuous magnesium sulfate component and water. So they are highly effective at combating acidity issues. They're very effective at reducing corrosion, both in the hot zones and the cold zones. And along with this, you can also get other benefits like reducing the acid dew point and reducing low temperature corrosion of the back-end pollution control components in the ductwork and the stack breaching, all those metal areas on the back cold end that might otherwise be susceptible to low temperature corrosion. So this is what magnesium treatments in fuel oil can do effectively, but we need to dig a little bit deeper to understand why and how these things work. If we can be armed with a little bit more detail, then we can start to draw some conclusions, not just on whether magnesium is good or not, but we can start to draw some conclusions on the kinds of magnesium treatments for fuel oil are the best to use. So first thing that we can see are slagging and deposit issues, boiler slagging problems. Now, Slagging, the term slag refers to a description of the buildup of some kind of deposit on boiler tube surfaces. These deposits typically are formed from the formation of fly ash particles. Generally speaking, when you burn heavy fuel oil, or when you burn coal or any kind of petroleum fuel, you'll get two different kinds of ash. You'll get the lighter fly ash, and you'll get the heavier bottom ash. So fly ash is the one that usually contributes to this boiler slagging most directly. Now, the fly ash particles, the fly ash hit the tube, they contain both unburned carbon, so a low level of unburned carbon, and they contain inorganic compounds. And inorganic compounds, we're talking about non-carbon compounds. We're talking about metals, things like sodium, vanadium, and nickel, aluminum, silicon, sulfur, all the stuff that was already present in the fuel before it was being burned. Now, slagging can be influenced by things like the combustion conditions in the boiler. It can be influenced by the fuel composition. How much inorganic, how much and what kind of inorganic composition that fuel oil has, and it can very much be influenced by the corrosive nature of the deposits that are going to be building up. So, with that in mind, let's consider a couple of variables that might influence slagging. First thing you see here, slagging problems can be V and O2 influence. In other words, they can be influenced by both oxygen levels and vanadium content. Now, we mentioned fuel oil composition. All fuel oil, since it's refined from petroleum, all petroleum contains a certain amount of vanadium metal. So all fuel oil contains a certain amount of vanadium. And the vanadium content in the fuel oil, that directly impacts slagging problems, because it will end up forming a vanadium oxide, shall we say, complex, some kind of vanadate. And the vanadate V2O5, that's the vanadate or the vanadium oxide that causes the most problems. And how much of this that is formed is really dependent on the excess oxygen level, or the oxygen level that's available in the boiler. If you have a low level of oxygen, a low oxygen excess, if you have a low oxygen excess, that's going to decrease the formation of V2O5. And thus it will decrease the problems with deposits forming that have low melting. And the converse can also be true. If you have a higher level of oxygen available, then you will probably have an increase in V2O5. And what you can see from this is this data here that's being displayed. This is an analysis of the percentage of different kinds of vanadium or vanadates, vanadium oxide complexes. This is an analysis of the proportion of different ones that are formed relative to the amount of excess air. Excuse me, I apologize for that. Sometimes when you got to sneeze, you got to sneeze. So you have 1% excess air, 3%, 4%, 5%, and then all the way up to 15%, which is very unusual, but it illustrates a point here. And then you have the blue is V2O5, and the red is V2O3 and V2O4 combined. Now, what you can notice here is that at lower excess air levels, you see lower levels of blue. You see lower amounts of V2O5 being formed. So the vanadates that do form are really skewed more towards V2O3 and V2O4, the ones in red. When you start getting above 3%, let's say around 3.5%, that balance really starts to shift. At 4% and 5%, you can see it is pretty predominantly V2O5 that's formed. And this is a problem because V2O5 has been shown to be really highly linked to corrosion problems in that boiler. In other words, if you have too much excess oxygen, or if you're forced to use too much excess oxygen, while that might help the combustion levels that you're getting, it's really going to contribute to some corrosion problems that you're really not going to like. Now, here you can see some illustrations here. You can see illustrations of slagging on heat transfer tubes, and the slag buildup tends to lower heat transfer and might cause undesirable temperature shifts. So these V2O5, these vanadium, these vanidates, and these sodium salts, they really do contribute to some serious high temperature corrosion problems. What they also do is they also catalyze the formation of SO3 from SO2. They increase your maintenance costs, because if you have them, you tend to have to replace tubes more often. It tends to be more expensive and more problematic to clean properly. And all of these contribute to a potential loss of production because you have to shut down more often to clean. And so you get lower boiler efficiency. So this slagging phenomenon is not something to be trifled with. It's not something that is really, that boiler operators really like to have to deal with. Now, here you see an illustration of what we would term a melted sticky ash. Okay, this ash deposit that is illustrated here, it has a melting point of 600 degrees centigrade. Now, 600 degrees centigrade, is that high or is that low? Well, consider that this kind of deposit tends to be, shall we say, sticky. You might even term it to be semi-liquid. It seems to be stickier. It seems to have a higher liquid composition in it, and that makes it stick easier and more tenaciously to metal surfaces, and that therefore makes it harder to clean off during surface intervals. Here are some examples of what some boiler deposits from heavy fuel oil look like. You've got some water wall deposits. You've got deposits in the superheater. These look like pretty serious depositions that the operators in these plants really are going to have to figure out what they want to do with. So, problems for HFO users arise in part when deposits or melting points are formed. When the fuel oil has the wrong mix of vanadium and sodium, that can mean that the metallic composition in the resulting deposits will give you low melting point slags that build up on metal surfaces. Now, what you can see here is you can see different vanadate or vanadium deposit compositions, and you can see what their melting points are. Now, remember V2O5, it has a melting point of around 675 degrees. When you add varying levels of sodium in there, like this one, this is the complex one that's got sodium, it's got vanadium, it's got oxygen, it's got more vanadium. This is a fairly complex vanadium deposit. It has an even lower point, 535 degrees. And then this one, NaVO3 combined with Na2O, 3V2O5, it's pretty complex one itself. It has an even lower melting point of 480 degrees. Now, contrast that with a simple one, 3MgO-V2O5. Somebody has taken magnesium oxide and added it to the mix, and the magnesium oxide has basically inserted itself into the deposit forming process. And the resulting deposit has a melting point of 1190 degrees, significantly higher. So that gives us a hint on what we want to use magnesium treatments for. Now, one other thing to keep in mind is that the proportion of vanadium and sodium in the fuel oil does play a part, or has a somewhat of a predictive quality on the kind of deposit that's going to be formed. Typically, the danger zone for forming a problematic deposit is when the ratio between vanadium and sodium is either between 1:1 and 4:1. In other words, 4 parts vanadium to 1 part sodium. If you can get to 5 or 6, say 6 parts vanadium to 1 part sodium, you're gonna have less of a likelihood of forming some of these most problematic deposits here. So now here, what we can see is how the ratio of vanadium and sodium in the deposits dramatically impacts or influences the melting points of the deposits that are formed. This looks at first like a rather complicated graph, but if you start to break down the various parts, you start to understand it a little better. What it shows us here is it shows us how the melting points of the complexes formed, how they can be dependent on the ratio of vanadium to sodium in there. In other words, the amounts of vanadium and sodium that came from the fuel oil content influences the physical characteristics of the deposits being formed. Now, what you can see here is, you can see down here, the x-axis here is vanadium to sodium weight ratio. It's a ratio by weight. You start at 0.1, you've got a 1-to-1 here, and then you've got a 10-to-1 all the way up to 101. And then that's graphed against the melting temperature or melting point temperature of the deposits that are formed. Now, what you can see here is that up here, the deposits that are being formed when the ratio is, let's say, 0.8, they're pretty high. These deposits are not going to be problematic much at all. But when you start approaching 1, and then as you go through really all above 1 through to 10, you've got some pretty problematic melting points here. They're around 600, they're between 550 and 650 degrees. This is the area where you get the most slagging corrosion problems. So what you should be, the takeaway with these past couple of slides is that the amount of vanadium content and the amount of sodium content combined with the amount of oxygen available, those three things tend to have a pretty big impact on whether the deposits that are formed in the boiler are going to be problematic with respect to corrosion or not. So when you have all of this, we've been talking about low deposit buildup. What's the solution to low temperature deposit buildup here? Well, the solution to these kind of harmful deposits traditionally has been using some kind of magnesium additive, injecting it into the fuel oil. The magnesium inserts itself into the deposit formation, as we saw earlier. It increases the melting temperature of those deposits. From a physical standpoint, it makes them more brittle, makes them more what they call friable, makes them drier even. And these dry deposits will be more likely to break up from the surface and fall off. And that's really what you want. That's the kind of deposit that you want. Now, if you use magnesium-based additives, you can really have a positive impact on problems, things like deposits, heat transfer problems. You can really help with high temperature corrosion and low temperature corrosion. You can help with opacity, and you can help with your maintenance. Now, here you see a couple of trial pictures here. Particular plant before the trial where they introduced magnesium additives into their fuel oil. You can see that on some of their metal tubes, they had some fairly substantial deposit problems. 3 months in, those same tubes are looking like this. Those deposits are being cleaned, they're falling off, they're not getting new deposits built up. Those tubes are looking a lot better. And then 6 months in during the trial, you can see that those tubes are looking pretty clean, Now, a couple of things you can take away from this. First of all, introducing a magnesium additive into an HFO system that already has deposits, those can actually be used to help clean up those deposits, not just to prevent new problematic deposits from being formed, but to help clean up existing magnesium deposits. And the second thing that we can take away from this is that it is not a short fix. These kind of deposits, they get formed slowly and they build up slowly over time. And so they are removed equally as slowly. So for a plant that had a deposit problem that was thinking, how long do we have to use a magnesium additive in order to expect results? You're looking at a good 3 to 6 months. But and if they say, well, that's too long, the answer to that will be, well, there's really, that is the way it is. Magnesium deposits are effective. It keeps them from having to go in and blast those deposits off manually. They don't have to shut down. They can keep going in operation, and those are distinct advantages. But it's not something that happens overnight. So we can see pretty clearly that magnesium additives, they do a number of good things for fuel oil users. But we have to consider the fact that not all forms of magnesium are created equal. Generally speaking, you have two majors of magnesium to choose from. You have a slurry or you have an oil-soluble formulation. Let's consider both of these and look at some of their pros and their cons. Now, if operators know that they need some kind of magnesium delivering treatment, the key question is what do they need to use? What form of magnesium do they need to use? And it is important for them to make the right choice. Now, first, the old school one, the traditional one was a slurry. They were magnesium oxide, or what they call mag-ox. It's kind of a white chalky powder. It's very cheap, very easy to manufacture. I mean, MgO is about as simple a chemical compound to manufacture as there is out in the world. They take that and they mix it into some kind of liquid and they create a slurry, kind of like when you're cooking and you create a flour slurry for thickening things. So they make a slurry out of magnesium oxide in some kind of carrier, and they deliver that into the fuel oil by injecting it into the fuel oil, and it delivers the magnesium that way. Now, the slurry itself would consist of pretty small particles, and so those small particles would be delivered along with the fuel oil. Those small particles only are what we call, they're only surface active. And they work typically by encapsulating the contaminants, encapsulating the deposit contaminants, so to speak. Now, the action of encapsulation, what this means is that if a mag-ox slurry will only work if it encapsulates the deposit, then it means that it has to be given time to build a deposit itself in order to treat the problem of anidates. And unfortunately, if you don't get the balance quite right, you can have some bad consequences for overall efficiency here. If you use too much mag-ox, you can get what they call a whitening effect, where you have an excess deposit that's formed, and that excess deposit is pretty highly isolated. It will keep the proper heat transfer rate from happening, and that will affect the efficiency of the plant, efficiency of the boiler. Now, compare this to how an oil-soluble magnesium system works. Oil-soluble magnesium, which would be either a carboxylate or a sulfonate, they work in a markedly different fashion, and we kind of try to illustrate that here. Oil-soluble magnesium can have a cleanup effect that we referenced earlier. They offer a cleanup effect benefit that you really cannot get from magnesium slurries, and that is a big deal. What you see here in this illustration is the oil-soluble magnesium is delivered along with the fuel oil, and when it reaches the deposits, it actually starts penetrating the deposits that are already on this boiler tube. Once the magnesium is penetrated, it then works to remove the existing deposits. And then over time, most of the old deposits, as you saw in those previous pictures, most of the old deposits will fall off because their melting points have been changed, their physical characteristics have been changed. They're no longer hard, sticky, semi-liquid. They're now dry and friable, and they tend to fall off on themselves. And what you get is a highly advantageous cleanup effect. And along with this cleanup effect, this means you're going to get better efficiency because your heat transfer surfaces are going to be a lot cleaner with oil-soluble magnesium. Now, another thing that magnesium does is it inhibits the conversion of SO2 to SO3. So if you can reduce that because you reduce less catalytic conversion of SO2 to SO3 when they come in contact with the vanadium deposits, if you can do that, you'll form less SO3, which means you'll form less sulfuric acid, which means you will have less cold end corrosion. And that is also a big deal for operators. Now, one of the main problems with magnesium slurries, liken them to a flour and water mixture that you're using when you're cooking. Unfortunately, one of the problems that magnesium oxide users have had to battle over the years is that they can tend to be hard on the systems that use them. They can be abrasive. And if you use them long enough, they'll do things like they will affect the nozzles of the burner tips. MgO, magnesium oxide particle, is not exactly soft. It's hard and it can be abrasive. And so when you take a whole bunch of those magnesium oxides and you make a slurry out of them, you've got a suspension of a whole lot of abrasive particles, and those wear out nozzle tips. You can see a graphical illustration here. A new nozzle, a new injection nozzle, has circular holes, but over time, those holes get worn by the magnesium oxide and they actually start to look more elliptical. And that's not really the way that this kind of nozzle was designed to function. So compare the spherical holes, the shape of the spherical hole with the deformed shape of the damaged holes. And what happens is that you no longer have the ability to properly atomize and combust fuel. Remember, these are the nozzles. These aren't the nozzles where the magnesium oxide is being injected. These are the nozzles of the oil guns for the HFO itself. And so over time, the magnesium oxide actually negatively affects the way that the fuel oil itself is injected into the burner. You don't get optimal injection, and that means you're not going to get optimal efficiency. You're going to get increased unburned carbon. You're going to get a higher level of coking particles, none of which are a good thing, none of which is an optimal situation. Now, a magnesium oxide slurry, because it is essentially a suspension of MgO particles. Those MgO particles, they are not petroleum soluble. That's why you have to make a slurry out of them. You have to deliver them in suspension in some kind of liquid and then hope that they stay dispersed in that fuel oil, because they do not dissolve into the fuel oil. They remain in particle form all the way up to the burner tip, all the way until they are injected into the flame front by those oil guns. And the implications for this are that you do not know for sure if your magnesium oxide slurry is dispersed at the same, shall we say, the same rate. It's not dispersed equally all throughout the fuel oil. So the rhetorical question is raised here: how do you, if you're a Magox slurry user, how do you know if the slurry is dispersed well enough and equally enough in the fuel oil that it works at the peak effectiveness that you want it to? And the answer is that you don't really know, and that is a problem for magnesium oxide users. The solution to this problem is to use a form of magnesium that is oil soluble, and that's the form of magnesium that's used in the ATX-1400 and 1100T formulations from Bell Performance. Both of those use oil-soluble magnesium sulfonates, high-quality sulfonates, which are readily dissolvable in the petroleum, and therefore, when the fuel is injected, the magnesium treatment is finally dispersed in the fuel, and you know for sure the dispersal quality that you're going to have. This means you're going to get a higher level of functionality. When the treated fuel reaches the combustion, reaches the flame front area, and it interacts with the ash contaminants. In other words, the magnesium in ATX-1400T is a lot more likely to do what you need it to do at a higher level than old school magnesium oxide slurries will. So all this, okay, so ATX-1400T. That 1400T is the 14% magnesium formulation from Bell Performance. Like we said, it's oil-soluble magnesium sulfonate, and it is really, really good at doing all the things that you use magnesium for. It fixes high-temperature corrosion. It fixes the molten deposit formations in the ways that we were looking at earlier. It reacts with the sulfur gas emissions, the SO2 and the SO3, to reduce low temperature corrosion in the cold end. It helps reduce sulfuric acid emissions, and it helps contribute to being able to better control stack opacity problems. And it does all of this in an oil-soluble base, and the quality of the magnesium sulfonate in the 1400T is approved for gas turbines. That's why it has the T designation. A lot of Bell Performance ATX formulations have been used predominantly in boilers, and when you're switching from a boiler or a furnace application to a gas turbine, you really have to up the quality of the magnesium that you're putting in there. The magnesium in ATX-1400T is approved. Its quality is high enough that it's approved for use in gas turbines. It is a turbine grade magnesium. The other formulation, ATX-1100T, has the exact same functionality as 1400T, but as you might be able to infer, it is not a 14%, it is an 11% over base formulation. Otherwise, you can say exactly the same things about it. It's oil soluble, it's gas turbine grade, it fixes corrosion problems, it interacts with deposits, it does everything that you need magnesium to do in heavy fuel oil, and it's suitable for use with gas turbines. Now, oil-soluble additives are markedly, or shall we say, markedly better. They work markedly better than slurries do. Here you can see comparisons with an old customer of ours that used to use magnesium slurries, and this is what magnesium oxide slurries. This is the kind of thing that they would have. These are deposits that they would have. When they switched over to magnesium sulfonate function ATX formulas from Bell, this is what they got. You can see much cleaner tubes, a lot fewer deposits hanging on to those tubes. A big, big difference. Again, same customer, different area, cleanliness when they were using magnesium oxide slurries versus the oil-soluble ATX formulations, marked difference between the two. So the difference should be pretty clear. Magnesium oxide may be cheap, but you get what you pay for. Oil-soluble magnesium sulfonates like ATX-1400T and 1100T deliver much, much better results. And those are formulations. The ATX formulations are manufactured by us, by Bell Performance. We are headquartered in Longwood, Florida. We have been in Florida actually since the early 1930s, when our founder, Robert Bell, moved us down from Virginia. He actually invented the world's first fuel additive, which was a detergent for gasoline and ethanol back in 1909. Bell Performance has been formulating heavy fuel oil treatment since 1952. So we've been doing this for a fairly long time. We have national presence throughout the United States in both direct sales and distributors, and we've always, well, really ever since the 1950s, we've always had a substantial international business as well. In fact, our ATX product line does substantial export business in the Far East, where they have a lot of industrial factories like glass factories, cement factories, ceramics that still use heavy fuel oil to fire their industrial processes. And a lot of those people will use ATX to treat their fuel oil. So we hope that through these slides, you've been able to see that there is a meaningful difference between traditional magnesium oxide formulations for fuel and the oil-soluble magnesium treatments manufactured by Bell Performance. We like to say that if you're using HFO and you have problems with it, then Bell's magnesium fuel oil treatments are the right choice for you. The ATX 1400T and 1100T, they are industry standard solutions that help you remediate and avoid a whole host of problems that both boiler and gas turbine HFO users don't really have any other choice to address. So that brings us to the end of our discussion. I hope that you've been able to see the value in what ATX 1400T and 1100T offer. If you have any questions, My email is here, ebjornstad@Bell Performance. Feel free to email me. Reference that you've been watching the ATX 1400 and 1100T presentation. If you have some questions, I will be more than happy to help you. This brings us to the end of our discussion. Thank you very much for joining me. Again, I'm Eric Bjornstad, Technical Information Director with Bell Performance, and we'll see you next time. Bye-bye.